Vincent today, Teets, and we were helping heads up display. According to the 2008 National Highway Institute, National Highway Transportation Safety Administration study, there was over 5,000 motorcycles fatalities a year. These accidents were 59% of the riders were wearing helmets, which is very low number considering the dangerous to riders in the first place. It was estimated that 1,800 lives were saved through the helmet use that year. Had fatal accidents of those riders been using a helmet, 800 of them could have been saved. From these studies, it is estimated that helmets are 37% effective at preventing fatalities. This seems like a low number, but it's due to all the accidents are considered, and not every accident the fatality was due to head trauma. In addition, rider distraction plays an important role. In an accident, we only have about 1.5 seconds to react, and while the rider is riding, they're looking down to check their speed. So this presents an opportunity for an accident to happen when they never have a chance to respond. Therefore, they need a device so that they can see their speed without being distracted. In this regard, student need, it needs to be a device to display data that can be easily read while operating a motorcycle, and needs to not compromise the helmet safety. For student need, we got our performance requirements. It needs to present readable data without requiring the rider to directly engage from the road. It needs to have adjustable brightness and contrast so that it's bright enough during the day so we can read it, while at night it's not too bright. At night it's not too bright for blind. It needs to display at a minimum speed as that's the most critical information we need while riding. It needs to also be low powered so that it can be usable by all riders, the leisurely rider, the commuter, and the long distance rider. It also needs to not compromise the helmet safety, as that would be the opposite of what we're trying to achieve. It needs to fit on the helmet without causing strain on the rider's neck.
Able to realize our needs and requirements, we devised our system architecture. Here we knew we needed a GPS in order to generate NMEA sentences. We also knew we needed a processor in order to parse these NMEA sentences. And we knew we needed a display to show the rider their speed. On top of all this, we also needed a power supply in order to power the entire system. For our processor, we chose something called the Beagle board. It has an ARM Cortex A8 processor running at 600 megahertz and 256 megabytes of RAM. We thought this was advantageous over a microcontroller due to its processing capabilities. With this, we also use something called the Beagle Juice, which is a proprietary battery used with the Beagle board. It supplies 5 volts. It also has another 5-volt header pin, so we could supply the rest of our circuit. For our GPS, we use something called the Jupiter 31. It's a low-power GPS. It draws signal from 20 different satellites and refreshes at a rate of roughly 1 hertz. We also used an external antenna with this to ensure that we had as much reception as possible. And our early prototyping, we utilized an Arduino Uno. We just used that for originally parsing the data from the GPS, and also it's convenient because it had 5 and 3 volts ready for us. For our display, originally we wanted to go with the bottom right, what's called a micro viewer module. It was a crystal that had a projector that would display the image within the crystal. We originally thought it was $400, but it ended up being that $400 is just the price of the crystal, and the projector was $1,200. So we decided to go with the iTop. We don't actually use it with the glasses. We just use a projector. What it does is it displays the projection at infinite focal length, so you can look at the road while still seeing your speed. Over here we have a circuit diagram of our translation circuit. Our translation circuit was used to communicate between the Beagle board and the GPS. Since the Beagle board used RS-232 communication, it expected plus or minus 5 volts roughly to communicate. However, the GPS used TTL logic levels, and that came around plus or minus 3 volts. So we needed this translation circuit utilizing a MAX232 chip to step up that voltage level. And you can see here we also have a voltage regulator in order to extract the 3 volts from the 5-volt power supply from the Beagle juice. Once we knew our components in our system architecture, we're able to devise a detailed design diagram. Here we have our GPS communicating with our Beagle board after going through the level translation circuit. That comes to the USB peripheral of the Beagle board. From there, the data is stored into the memory card and is also parsed. The parsed data is converted into a composite video via the S-video peripheral on the Beagle board, and that S-video is sent out to the iTop display converter box, which converts the composite S-video to QVGA, which gets displayed through the iTop. And this entire system, excluding the iTop, is being powered by the Beagle juice. Over here you can see our initial integration of all the parts. This is prior to it being mobile. We're still pulling 5 and 3 volts off the Arduino. However, later we implement everything in a box, except for the iTop. And the box measures approximately 20 by 15 by 8 centimeters. It weighs approximately 1 kilogram. Here we hired a professional model to demonstrate what everything looks like. Put the bonds inside the backpack, and the eye-top is actually mounted onto the helmet via Velcro. We decided to use Velcro because it's a little easier, and we're able to adjust it depending on the rider's facial structure and height. We also tested this up to 45 miles per hour, and nothing flew off, so doing okay.
In order to use the information displayed on the GPS, from the GPS on the eye-top display, we needed to write a GUI program, which we use the Python programming language for this. We take these NMEA sentences here and we convert them to speed in miles per hour and cardinal direction heading. Before we receive a GPS lock, we display here in the upper left-hand corner this no lock message to inform the user. When our device is powered on, we wait for the GPS lock. During this time, we display the no lock message. When we receive the lock, we first write the NMEA sentence to the GPS log file. We parse the sentence. We pull the speed and the heading out. We convert the speed from knots to miles per hour, and we convert the heading from degrees to the cardinal directions. After this, we update the display. In order for our GUI program to run on the video board, we needed to install an operating system. We used 3 different operating systems before finally settling on Arch Linux. The first operating system we used was Ubuntu. However, this is a mostly desktop operating system, so it used very large amount of the RAM, almost all of it, and it used about 1 gigabyte worth of disk space, so this was unusable for our project. After doing some research, we came across Angstrom Linux, which, as the name implies, it's a small, lightweight operating system. It's very quick, so it met our design needs. However, it was actually intended to run on the Beagle board. So because of this, we were able to get the video to work properly. However, one of the issues we had was that we were not able to get onboard serial ports to work properly. So our plan B was to use a USB to serial adapter, but in order to use this adapter, we needed to install a driver, and the package manager that we were going to use to install this driver doesn't resolve dependencies, and we weren't able to figure out why it wasn't able to install the package properly. So afterward, we did more research and we came across Arch Linux, which is a minimalistic install. It only installs the kernel and necessary drivers. So this met our requirements for a small, lightweight operating system. It included an easy-to-use package manager, which resolved dependencies, which allowed us to install the X display server, the OpenBox window manager, as well as Python and the TK-Engine library. One of the issues we faced was that the font pack was not installed by default, so the GUI didn't work properly when we put it on the Beagle board. However, we were able to easily install this package and resolve this issue. The main issue we faced was that the X server did not, there was an issue with the display driver with the frame buffer, so it did not advertise itself to the X display server. So we had to edit the XOR file by hand in order for the frame buffer to be used. Afterwards, we were able to implement all the necessary functionality, and we had implemented the project, the main functionality of the project.
After we got the whole system integrated and functional, we moved on to testing. So we did several qualitative and quantitative tests, the first of which being that we took our system on a ride in a car around Patriot Circle. While we went, we displayed the speed, but not only that, we also logged on our memory card the GPS and the speed data. We compared the speeds to the speedometer of the car and verified that we were getting accurate measurements of speed. In addition, our project needed to be of low power consumption. Our Beetlejuice power supply provides 4,500 milliamp hours, and our peak usage is 900 milliamps. Now, that's not the constant usage of our system. However, in the worst case scenario, if it were to continually run at 900 milliamps, we should get about 5 hours of use. We left our system running for an extended period of time, and after 6 hours, it was still running and functional, and we decided to end the test there because there shouldn't be too many motorcycle rides over 6 hours. Additionally, we had a motorcycle rider try our system on a closed circuit track, and they were able to easily see our display without diverting their gaze from the road or being too distracted. So we got the motorcycle rider approval. Now I'd like to show you a video of our system working. In the top left, you can see our GUI. It'll show you the speed in miles per hour as well as the heading. This was an earlier version of our GUI up here. As you can see, it doesn't say the miles per hour as it did in the previous slide, as well as the heading is not on the cardinal directions. In the top right is a video of the speedometer of the car, as well as the front view. So you can see us going around Patriot Circle here. And as we come up to pedestrians, speed bumps, stop signs, that sort of thing, you can see our speed decreasing. And if you notice on our GUI, it updates every so often, and you can compare that to the speedometer of the car and see that we are getting accurate results. So we began our trip at the engineering building at the handicap loop and came back around. There were some obstacles along the way, as you can see here. Not quite sure what was happening, but everything was okay. And here we are arriving back near the Shenandoah parking lot. All right. So as I mentioned, we also kept track of the GPS data. So the user of our system can take the memory card out and plug it in the computer and run the program that we've written that will parse the data and plot it on Google Maps. So our trip here began at the engineering building, went all the way around Patriot Circle, and we came back. This is just a zoomed in view where we plotted the speed data points as we went along. So to evaluate the success of our project, we wanted to verify that we met all of our initial requirements. So we had a system that did not divert the rider's gaze. We didn't compromise the safety of the helmet because our mounting system, we didn't have to drill into the helmet or compromise it in any way. We displayed the speed. The iTop display also has adjustable contrast and brightness, as well as we met our low power consumption requirement. And because the iTop was the only part that was actually mounted to the helmet, we didn't cause any undue strain to the rider's neck. Further expansion we see for our project would potentially be going into GPS turn-by-turn navigation or getting additional motorcycle diagnostics from the bike, such as RPM or the tire pressure sort of thing. We'd also like to work with a helmet manufacturer so we can actually have our system integrated within the helmet. That way we don't have to worry about compromising the integrity of the helmet, but still having space to fit our system completely within the helmet. And to do that, we would take all of our components and PCB and get a smaller package. The way that we facilitate future expansions is that we chose to use the Beagle board rather than just using a microcontroller. This gave us higher processing speeds, as well as it has an expansion header where we can connect daughter board, that sort of thing if necessary. Man hours spent on this project ended up being around 426 hours. The system cost was about $471. The reason it's different from our cost spent was that we did have some parts that were donated to us. And this is just a breakdown of our individual contributions on the project. We estimated the total project development cost based on the mean starting salary for an electrical engineer being around $62,000. So our project development cost ended up being around $13,000. Lessons learned during the project were that we should research everything before we get started with experimentation, how the components are going to interact with each other. It helps a lot if you know everything about them before you get going. We also had a lot of experience with teaming and inter-team communication, as well as time management, making sure that we kept on our schedule and made sure that we made all of our deliverables. We'd like to thank our faculty advisor, Dr. Lori, and also special thanks to Dr. Capps and Dr. Guy, as well as Professor Lilly for sitting in on presentations this past year and giving us valuable advice and feedback. We'd also like to thank Kevin Nicotera for advice on the Linux operating systems, in particular getting S-Video to work with the Arch distribution, as well as Joel Chenette for donating the Beagle board for our use on the project. and Richard Lee for driving us on all of our tests. At this point, I'd like to open it up for any questions, comments, or concerns.
I cannot use this device because there is no radar detection. Any questions? Come on, with
Okay, so I assume one of you
My family has motorcycle
Okay,
riders in it.
good enough. So in terms of actually defining the need, okay, how did you come up with the need, the GPS? Is this something that you all, as a function of being able to do it, decided to do it? Or is this something that was a need for the staff?
The reason why we decided to use the GPS was that we wanted to have the capability of going towards GPS turn-by-turn navigation, even if that's not implemented in our project. That way, we don't have to switch to a completely different system.
Yes. So we saw a wide shot of the helmet on your paid model. We saw a close-up of video driving around campus. But where's the picture of what the thing looks like if you were to see it live? In other words, we saw you driving around the car with that, but what would a rider see? In other words, pictures of the helmet.
Correct.
In
I
close.
have the helmet right here for you.
There you go. Why didn't you bring it out?
Mr. Young, they will put you in the motorcycle.
So we got the helmet right here.
Oh, that's cool.
The reason why we don't have the video, we had the screen capture of our system, is that it's very difficult to have the system running and hold the video camera inside the helmet for you.
Okay. I'll be honest with you, it looked like you were doing a dummy demonstration until I see it. Right there. Okay, got it. Good.
Here is a question.
You said that the only thing you attach to the helmet is the wristband. Everything else is in the box that the rider can have its backpack. Does that include the GPS receiver module? And it receives inside the backpack inside the box?
Yes, there's an antenna now. We have a metal plate in there. The antenna's not for better seeing the light in the box.
One more question.
Yes.
Did you guys measure the limitation of the GPS in case if the biker has to go to tunnels? Do you know how this is going to be?
We don't know. We haven't extensively tested it. We tested it just around here. We know we purposely chose a device that was easily able to pick up signals, and also we chose an external antenna to ensure that we had that. There were times where it seemed like we should have got signal where we didn't. For example, immediately outside the engineering building at the Trop, the smoker's place. And that didn't really have signal there, but right when you walk outside, especially with the antenna, because it's also magnetic, you're able to attach to other metal pieces, and it extends the antenna surface, so that helps a lot too. But as far as extensive testing, not so much.
Additionally, the GPS at any one point is in view of 20 satellites, which is much higher than a lot of the other GPSs, as well as it's meant for use in low signal environments, like in parking garages and that sort of thing. We did go through Shenandoah parking garage, and it did maintain the relative distance between two data points. When we looked at our GPS plot, it actually showed us going through Research 1 when we were in the parking garage, but it actually still maintained for our system the speed because the distance between the two data points was still valid.
Thank you very much.